Well, gases are not the only things that are involved. Gases and aqueous things are what we've been talking about so far. What about reactions involving solids or liquids? These are common in reactions. You can have a pure solid or a pure liquid as a reactant or a product. Here in this example, we're looking at carbon monoxide reacting and forming carbon dioxide and carbon. And so then the carbon is a solid and is just sitting there at the bottom of this container. The concentration of a solid or a liquid, pure liquid or pure solid, doesn't change. Now, you can calculate a molarity, say, for water, using the density, right, and the molar mass and stuff, and you can calculate how many moles would be in 1 liter of water, and it's about 55. But whether you have a little bit of water or a lot of water, the concentration of the water in pure water is the same, right? Same thing with a solid. It's not diluted with anything, so it's always going to be the same. So solid and liquid concentrations don't change, and so anything that's a solid or a liquid is just not included in the equilibrium constant expression. So here, you have 2CO going to CO2 plus C. Regardless of whether there's a lot of carbon in here, or, I'm sorry, that's a little bit or a lot, the concentrations of carbon monoxide and carbon dioxide under these bell jars is going to be the same. And if we wanted to write the expression for that in terms of Kc, it would be the concentration of the product divided by the concentration of the reactant squared because of the 2. The solid doesn't change its concentration, so it doesn't need to be included. This is something that made things a lot easier also. So let's write the equilibrium expression for this reaction between carbon dioxide and water. Well, it just says equilibrium expression. It doesn't specify pressure or concentration. Which one should we use? We should use concentration. Because these are aqueous, and so expressing that in terms of partial pressure is going to be rough. We can express the concentration of a gas in moles per liter. It's just the pressure divided by RT. So we're looking at Kc here. And so we're looking at the concentrations of the products. So we've got H plus, coefficient is 1, times HCO3 minus, also with a coefficient of 1, divided by what? The concentration of CO2. The concentration of water doesn't show up because it doesn't change. Any questions? Yeah.
The slide previous to this one,
Mm-hmm.
the carbon monoxide one, don't we use, so should we use the 1 kp or kc?
For this one with the gases, you could use Kp or Kc. Yeah. The Kp and Kc are not equal for this because there's 1 mole of product and 2 moles of reactants in the gas state, but they're just related to each other by factors of RT. So it kind of depends on what information you have available, what's more convenient. Right, an equilibrium expression, constant here, Kc, for this chemical equation? What's it going to be? Just the concentration of CO2. This is a gas. These are both solids. Solids don't get included because their concentrations don't change. So this equilibrium constant is just the partial pressure of CO2. The molarity of CO2. How about this one? So this is a liquid, right? So we're not going to include that. This is a gas, so we'll use that one. And you square it because there's two of them. Divided by. And both of these are gases. Of HCl to the fourth power times O2. Okay? This is something that is simple, but it can mess you up in calculations because you write out the equilibrium expression and you forget to leave the liquids and solids out, and then it gets impossible to solve. So here we have heterogeneous equilibria. We have solids, gases together. Which one of these is going to have Kp equal to Kc? I have a vote for B. Yeah. We're looking for equal moles of gases on each side. And so that's this one. So that doesn't count. There's 3 moles of gas. This doesn't count. 3 moles of gas. Okay?